Let's talk about one of the biggest, most powerful ideas in all of mathematics, the derivative. It's this incredible tool that lets us figure out how something is changing at one single tiny instant in time. It's a concept that shows up absolutely everywhere, from physics to finance, so let's just dive right in. To get our heads around this, think about a simple question. How fast are you moving right now? I mean, if you're driving, your average speed is easy, right? You just take the distance you drove and divide it by the time it took. But what about your speed at this exact moment? How can you measure change when the amount of time that's passing is, well, zero? And see, that's the impossible question that the derivative was invented to answer. Normally, to get a rate of change, you need a change in something over a change in time. But if that change in time is zero, you're trying to divide by zero. And as we all know, you just can't do that. But it turns out calculus has this really clever way around the problem.
Geometrically, here's what we're really trying to do. We're trying to find the steepness, the slope of a curve at one specific spot. So picture a graph of your car's position over time. If you were to zoom in on that curve, closer and closer and closer, eventually any tiny little piece of it is going to start looking like a straight line. The slope of that tiny little line? That's the instantaneous speed we're looking for.
So how do we actually find that slope with math? Well, this brings us to the formal tool that was built for this exact mystery. It's time to introduce the star of our show, the derivative.
Okay, I know what you're thinking. That formula looks a little intense, right? But don't worry, this is what's called the limit definition of the derivative. And all it's really doing is describing that zooming in process we just talked about. It's calculating the slope between 2 points that are ridiculously close together, and then it asks, what does that slope get closer and closer to as the distance between the points, which we're calling h, shrinks all the way down to 0?
So what's the big takeaway here? This one formula really does two incredibly powerful things. First, it gives us the slope of the tangent line. That's the line that just barely kisses the curve at one single point. And second, that slope is the instantaneous rate of change. This is the very idea that lets us calculate everything from the velocity of a rocket to the tiny fluctuations in the stock market. It's a huge deal. Now, to really see how this thing works, we've got to get our hands dirty. We're going to walk through an example, and we're going to do it the hard way first, using that full limit definition. It's so important to see what's happening under the hood before we jump to all the cool shortcuts. Here's our function for today. It's a parabola, so it's a nice curvy graph. Our mission, should we choose to accept it, is to find a new function, we'll call it f prime of x, that acts like a little slope-finding machine. It'll tell us the slope of this curve for any value of x we can dream up. All right, here we go. We're just taking our function and plugging it straight into that big definition we saw a couple slides back. That first chunk is f of x plus h, and the second chunk is just f of x. I know, it looks like a complete mess, but trust me, the algebra is about to do something really neat. Okay, now for the cool part. After we expand all those terms up top and start simplifying, watch what happens. Every single term that doesn't have an h in it just vanishes. They all cancel out. And that's not a coincidence. This thing is built to work this way every single time, leaving us with only the terms that have an h. And this, right here, is the key that unlocks the whole puzzle. Since every single term left in the numerator has an h, we can just factor it out to the front. And that lets us cancel the h on top with the h on the bottom, the very h that was causing our dividing by zero problem in the first place. With that problem causing h totally gone, we can finally let h go to 0. That 2h term just disappears, and we are left with our answer. The derivative of our original function is 4x minus 16. We've built our slope-finding machine. Now, let's be honest. Doing that whole algebraic dance every single time would be a lot. So the great news is, because that process is so predictable, mathematicians used it to figure out a whole set of super powerful and elegant shortcuts. Yeah, the whole reason we went through that long process was to understand the why behind it all. But now that we get it, we can use these amazing differentiation rules that were built on top of that foundation to find derivatives way faster. So let's start building our toolkit. These are the absolute fundamental rules you're going to use all the time to find derivatives, and you won't need that big limit definition every time. Here are the first two heavy hitters. The constant rule is super easy. The derivative of any plain old number is just 0, which makes sense, right? A graph of a constant is just a flat horizontal line, and its slope is always 0. Then we have the power rule. This one is the real workhorse. To find the derivative of x to some power, you just bring that power down in front as a multiplier, and then you subtract 1 from the original power. That's it.
And check out just how flexible this power rule is. It works for a nice whole number power, like x to the fourth, no problem. But if you rewrite 1 over x as x to the negative 1, or the square root of x as x to the 1/2, the exact same rule still works perfectly. It's just an incredibly efficient little tool.
And finally, the sum and difference rule is, well, it's pretty much what it sounds like. If you have a bunch of terms being added or subtracted, you can just take the derivative of each little piece all by itself. This is what lets us use our simple rules on functions that look a lot more complicated, just by tackling them one term at a time.
So let's bring it all home. Whether we use that long, complicated limit definition or these super fast shortcut rules, we always end up at the same single core idea. The derivative of a function is just a way to measure its rate of change at one specific point. It's the ultimate tool for measuring instantaneous change.
We've built a really solid foundation here. You now get what a derivative actually is, and you have the basic rules to find one. But that leads to a final little question to chew on. We can handle adding and subtracting, but what happens when you need to multiply or divide two functions? Well, it turns out there are special rules for that too, and they open up a whole new level of calculus.